Let's continue on with the theme of the morning. We have Ben Sanderson next from NCAR, from CGD, which stands for Climate Global Dynamics.
Yeah.
Are those the letters? Excellent, yep. PhD from Oxford, he reports, and a cycling enthusiast. In case you want to chat him up about good rides around here, I would imagine. Save that for after the talk. As usual, feel free to ask questions. Ben has politely indicated he'd be happy to take questions at any time, and then the last half hour we can devote specifically to questions. I think that about covers it.
Yeah,
so
cool.
Thanks.
Right, so my remit is probably smaller than this talk would indicate. Because this is a massive topic which is going to be covered over the next 2 weeks. So I'm going to concentrate specifically today on ensembles, both perturbed physics ensembles and multimodel ensembles of GCMs. And I'm going to do this by going through papers from studies from various people, and quite a lot of these are concentrated on the idea of constraining climate sensitivity. But don't take that as an indication that that's the only thing you can do with perturbed physics ensembles, or with the examples I'm going to show you. It's just, it's a convenient metric to show how, if you're interested to know an aspect of future climate change, how you deal with the output of these ensembles. So it's just a number, something you're interested in. And so the field is wide open for you to do whatever you'd like. So I'm going to start by talking about the things which I'm not going to talk about, which other people are going to talk about throughout the rest of the week. The first thing which I'm not going to talk about at all is what humans are going to do over the next 100 years. This is somebody else's problem, and this will be covered later in the week. So, is it going to be covered later in the week? Right, good, yes. Clearly humans could take various choices in terms of how they mitigate or adapt to climate change over the next 100 years, and that would result in different greenhouse gas emissions and different aerosol emissions, and that will change the future we observe. I'm going to ignore all of that, and I'm going to concentrate on what happens if we follow a given trajectory. What does the planet do in response? Secondly, I'm going to ignore almost entirely initial condition uncertainty and natural variability uncertainty. So this is also going to be covered later in the week. So this is the idea that if you make a tiny perturbation in a model in its initial state, within a year, or definitely by 5 to 10 years, the model will have completely forgotten what that initial state was. And so you have a range of possible outcomes which you could have, and then that carries on for the rest of your projections. So the types of simulations which I'm talking about are on a 100-year timescale, and you have to imagine that we've averaged out all of those different choices which we've made in the initial conditions. So what are we going to talk about today? So the first thing I'm going to talk about, probably for the first 2/3 of this talk, is perturbed physics ensembles. And this addresses the problem of what happens at the scales smaller than the grids which are represented in a GCM. So here is the state of Wyoming, and it's shown to show the scale of various different GCM grid boxes. Up until the CMIP3 generation of climate models, the resolution of the models on average was somewhere around the 2-degree mark, so a big state. And if you look at all of the structure on this satellite image, which happens at a scale smaller than Wyoming, clearly there's a lot of assumptions which are being made about the behavior of the model at a scale smaller than this. There's convective cloud systems, fronts can come through, and as you look across the image, there's various different things going in different regimes. All of this has to be captured as a statistical approximation within that grid box. All of the state variables within this grid box are represented as a single thing, and all of the diversity within that has to be represented using parameterizations in the climate model. And so these parameterizations for convection, for example, might assume that there's various different convective plumes over the ensemble, and they want to assess whether there's enough available potential energy to trigger convection in the grid cell, but this is going to be represented statistically. If there's a variation in the topography across the grid cell, this is not explicitly resolved. So it could be mountains on this side of the grid cell and plains on this side of the grid cell. This diversity has to be represented through parameterizations. And as you move to higher resolutions, the number of assumptions which you have to make to some degrees goes down, but it doesn't go away. And actually, as you go towards very small resolutions, perhaps smaller than this is sort of our cutting-edge resolutions which we're running with at NCAR today. But if you go to much smaller than this, perhaps a tenth of a degree, then you start running into problems, because the statistical approximations which we've made about the distributions of clouds and the diversity of behavior which you get within a grid cell begin to break down when you get to the scale of an individual cloud. And so when we get to that point, we're going to have to reconsider the way that we approach the climate model. We won't get it for free by simply reducing the resolution anymore. We're going to have to think explicitly about how to get past this point, because tenth of a degree isn't enough to actually resolve the clouds themselves, but it is enough to mess up what we're doing at the moment. So, parameterizations. There are lots of them. So if you consider all of the different components of the land model, all of the different components of the climate model, there are parameterizations which determine how humid it has to be before it rains, how unstable the column has to be before you trigger convection, the convection on a shallower scale in the boundary layer, and then in the land surface, there's parameterizations on how carbon is allocated to leaves, on the efficiency with which light can pass through the canopy of a rainforest. Each one of these things represents a dimension of uncertainty in the climate model. And each one of these things, some of them, if you're lucky, can be measured. Some of them relate back to a thing which you can go out in the real world and then measure the thing which you're interested in. But often that's not the case. Often the things, the parameterizations, the actual uncertain numbers in the climate model are to some degree empirical. Or the observations which you can make only make sense when you look at the bulk properties of the climate model. So say if you're tuning the critical relative humidity to form a cloud, then the way that you would actually assess whether you've got that number right is to look at large-scale distributions of clouds on a planetary scale, and then change that number until you have a distribution of clouds which you're happy with. This is not something which is usually done by explicitly, or it can be done by explicitly flying aircrafts through clouds and measuring when you get clouds at different humidities, but that's not the way it's done in general with most GCMs. And so this creates, when we're interested in using these climate models to produce projections of future climate change, this creates a problem, because the decisions which we make in choosing the parameterizations for which go into these uncertain, to some degree uncertain processes in the climate model, can directly impact the result or the projection which we get if we simulate the trajectory of the Earth's climate for the next 100 years. So we can either ignore this, which is often what's done, or we now need to think about a way of systematically exploring this space and assessing whether these choices which we make in the tuning or parameterization choices of the climate model, to what degree they impact the future climate change which we're simulating. So let's start with an idealized case. Let's imagine that you have a climate model with two uncertain parameters which you've, for one reason or another, decided which are important to the climate variable which you want to measure the uncertainty in the future. So the first thing which you might do is just, say this is the default value of both of those parameters. You might just try changing each one of those one at a time. You can do this with lots of different parameters. You can use 30 parameters from the model and do this. It's cheap, and you can get the first order representation of the parameter sensitivity of your climate model. The problem is it's not always that simple. Sometimes the behavior of the climate model might be that in a single dimension, say if you're looking at climate sensitivity or how much the global mean temperature of the Earth changes in response to a given greenhouse gas forcing, and say we're looking across changing P1, you might find that it's a nonlinear function. Maybe it's a quadratic. If you take 3 points, a straight line might not fit. Okay, so now we need to sample slightly more points in our two-dimensional parameter space. But then it could get even more complicated than that, because you might find that parameter 1 interacts nonlinearly with parameter 2. And so now, to assess the quadratic uncertainty in 2 parameters, we now need 9 points in this two-dimensional parameter space. So you can get away with sampling your parameter space like this if you have a small number of parameters. And this is some of the early experiments, like the climateprediction.net experiment, had 5 or 6 uncertain parameters in the model, which were relatively well chosen. I mean, it helps if you speak to model developers before you start doing an experiment like this, because they invariably have a gut feeling on which parameters will affect the processes that you're interested in the future. So you can cheat this curse of dimensionality. But if you went and looked at the CESM and you decided there were 32 parameters that you were uncertain about, then, I'll explain what this is first. So if, say, there was only 3 parameters that you were interested in, you could perform that experiment, and then you could form these nice nonlinear quadratic surfaces within the volume of the 3 parameters which you were interested in. So these are contour surfaces of climate sensitivity for 3 parameters within the previous version of the community atmosphere model. And so you can see these nonlinearities manifesting themselves. So in order to get a high value of climate sensitivity, you need a specific combination of these 3 parameters. So you need this parameter to be small, you need this parameter, and you need, I can't interpret it from this angle, but it's complicated and it's nonlinear. And it doesn't actually matter what the parameters are for the point which I'm trying to make. So you can get away with doing this for 3 parameters, maybe 4, maybe even 5. But if you have 32 parameters and you try to do this type of approach, it would take more than the entire production of the Earth's energy for the next 3 million years. I'm assuming that we carried on producing energy at current rates. So we can't do it like that, clearly. So we need some tricks. So the first thing we need to do is abandon the idea that we can sample every single corner of the parameter space. We can't do it that thoroughly. So we need to find intelligent ways of sampling the parameter space in the best way we can for a given number of with a given number of simulations. And there are various ways to do this. I'll just talk about one. One way of doing it, which is a common way of exploring a high-dimensional parameter space, is to use a Latin hypercube, which means that, say you had the 2 parameters as before, but you only had enough computing time to run 3 experiments. The one sensible way of running it would be to choose your parameters such that with your 3 experiments, you'd sample 3 different values of each of the parameters. And so you can produce these magic squares which effectively do that. And this can be extended to as many dimensions as you like, and it's a relatively good way of making sure that you get into at least some of the corners of the parameter space and you get a diverse range of responses. If you just did the most obvious thing and you just sampled like a multivariate Gaussian distribution in all of your different parameters, then you might what you end up once you have a large parameter space is that a lot of the parameters a lot of the experiments which you run in the ensemble effectively are much closer to the center of the ensemble, and you find it very difficult to get into the corners. And so this is a good way of getting a diverse range of behaviors in your ensemble. So assuming that you've produced an ensemble and you've used some sensible parameter sampling approach to produce some future climate simulations with a range of different parameter combinations for your model. What do you do with it? So let's say, again, you're not tied to using climate sensitivity, but let's say you were interested in climate sensitivity. And the first thing you might do is just produce a histogram of the output in your ensemble. And so you might have sampled 100 different parameter combinations in your model. Each one has a slightly different value of climate sensitivity, and then you can just plot a histogram of the responses which you get within your ensemble. Now, there are various reasons you can't interpret this as a probability distribution. A lot of the parameters in your ensemble might not do anything. And if you've used a sensible parameter sampling approach, this shouldn't matter too much, because if they're null, but you've used a sampling such that you've optimally sampled your entire space, then it shouldn't matter that one of the dimensions is null. But fundamentally, the prior, i.e. the arbitrary decisions which you made in sampling your parameter space, when you look at the distribution that causes in climate sensitivity or in the variable you're interested in, doesn't really mean anything. You have to transform this into a prior or into a distribution which does mean something. The second problem is that you've, at this point, sampled your parameter space. Let's say you have 30 parameters you're interested in. You've sampled your parameter space in an incredibly sparse way. So, again, if you've used a sensible technique, like Latin hypercube sampling, you will have a long tail of responses because you'll have lots of models which are doing weird things because they're out in the corner of the parameter space. This doesn't mean that this is representative of the likelihood of those weird futures happening. So the first thing we have to do is get over the problem that we've sampled the parameter space in this sparse and strange way. And the standard way of doing this is to utilize a model emulator. So an emulator can be anything you want it to be. I mean, an acceptable form of model emulator would be a multivariate regression. All it has to do is relate the input to your model. So that's your choice of parameters in this case, to the thing you're interested in, which in this case is climate sensitivity. And so a simple emulator would be simply to do a multivariate regression relating the parameters, the set of 32 parameters, against the climate sensitivity. But this would not be a good emulator because it couldn't represent the non-linearity in the way that the parameters interact, or the non-linearity in the response of any given parameter and climate sensitivity. And so there are various, and thirdly, it's difficult to get the appropriate measures of uncertainty in the performance of your emulator. So you might want to do something more complex. And there are various ways of doing this. You could use neural networks. You could use random forests. You could use Gaussian process emulators. I'm not going to talk about any of them, the details of those now. You're perfectly capable of looking at the appropriate MATLAB function. But each one of these effectively will produce a nonlinear transfer function between the parameter choices and the thing you're interested in. And if you use an approach like random forest, then it will produce an ensemble of different transfer functions. And so encoded within the transfer function itself will be some assessment of the uncertainty in the emulator which you have. And all of them, to some degree, you can choose a training set and you can choose a validation set. So you can assess internally within your prediction how good your emulator is at relating your parameter choices to the output of the model. But once you build that emulator, sorry, what a question?
I just want to make sure I understand the concept. So the idea that you're with the model emulator that you are, instead of having to use the full process, So is the idea with the model emulator that instead of having to use the full physical model to get from this parameter to this outcome, you're basically like some numerical or statistical model that I guess is simpler and quicker, or am I misunderstanding it?
Yes, no, that's exactly right.
Okay.
So, and orders of magnitude quicker. So, I mean, the GCM simulations which go into producing this. Say you want to know what climate sensitivity is, that probably requires at least 45 years of simulation for of a model with a fully resolved atmosphere model and at least a slab ocean. And you can run an emulator in a fraction of a second. So once you're confident that you've captured the relationships between the parameters and the thing you're interested in, then you can stop looking at the actual model. But you can never get the full physical intuition from an emulator. It's just a relationship. But what it does allow you to do then is it allows you to sample your parameter space in a very dense way. So then you can choose whatever prior you'd like and then run the model tens of millions of times, or run your emulator tens of millions of times. And then you can look at the distribution of all the possible models and all the possible responses which you might get by choosing different points in your parameter space. And so, whereas before you had this sort of blocky histogram, you now get a smooth response of all the possible climate sensitivities which you could get within the parameter space of the model, with some uncertainty which comes from the internal predictions which your emulator is making. But you have to be careful, because now you have your all-powerful emulator, and you're able to effectively reproduce the results of the climate model at will. Your results are still dependent to some degree on what prior you choose. So if you choose a prior which is, so say you have a parameter, you decide to sample a parameter linearly. So say the parameter goes between 0 and 10. Or let's say 1 and 100. Depending on the parameter which you're choosing, it might be appropriate to sample that with a logarithmic distribution, or it might be appropriate to sample it with a uniform distribution. And that's going to change the distribution which you get when you look at the distribution of the quantity which you're interested in when you run it through the mill and you run your emulator with this prior. So your prior matters. And even after you've put it through the Bayesian sausage machine, it still potentially matters what prior you've chosen. So you have to be cognizant of that. And that was, this was an early paper stating that process, stating that without going through the Bayesian sausage machine, that if you simply choose different priors, some of which scale with sensitivity, some which scale with 1 over sensitivity, then you get very different distributions for climate sensitivity. So, question?
Does all the emulator just take into account of the interactions between all the parameters that you feed into the emulator?
Should do. Well, it depends whether your ensemble is well sampled enough to sample those interactions. If it is, then yes, the emulator will reproduce those. If you choose an appropriate emulator which can capture the nonlinearities, and you should be able to validate that by holding some fraction of your ensemble back and making sure that you can predict what the outcome of those members which haven't been used yet was. So yes, there's no reason if you choose a neural network or a Gaussian process emulator why you can't capture the nonlinearities between different parameters, yes.
But there's no clear way for you to find out what those interactions actually are, because those are like black boxes that you feed into.
Yes, no, it's a black box. But if your black box can capture a nonlinear process, then you can represent it. It doesn't help you understand it, but you can represent it.
Okay, thank you.
So, if your climate sensitivity distribution is so sensitive to the prior that you choose, do you think the results are meaningful? And I mean, do we know enough about the distribution to basically say what type of prior we should be choosing?
Not necessarily, no. I think intuition, I think physical understanding of the climate, the process which goes into the parameter is important on this point. I mean, if you're using a prior which is defined in the parameter space, and you go and talk to the model developer, and they say, I mean, often if you get the minimum possible value, the mean value, and the maximum possible value, you get a good feeling for whether that's going to scale, or whether that should be a uniform prior, or whether it should be a highly skewed prior. But no, I mean, it's a problem. It's a problem with this methodology that with approaches which have fundamentally are dependent on, like UKSIP, dependent on the choice of prior. It's an uncertainty which isn't necessarily characterized within the results.
And I think the second question would be then, does it necessarily give you physically meaningful results? Do you come up with physically meaningful sets of parameters through this type of method? Can you come up with climate models that just don't make sense in terms of parameter combinations?
Oh yeah, easily, trivially, yeah. So
how do you get rid of those out of your, or do you not?
Haven't talked about that yet, but yes, that's the next problem. But I mean, to answer, like, if in the climate prediction.net ensemble, there was some significant fraction of the models which started developing sea ice in the tropics. It's there's massive the number of models which are actually potentially comparable or better than the default configuration of the model is a fraction of the ensemble. The majority you can disregard.
About a quarter of them are...
It depends. I'll talk about. I'll get onto that. Now, so the issue is that you can't trust all of the models in the ensemble. And if you look at, so this is an ensemble which we produced with the NCAR model quite recently. The big red dot. So this is called a Taylor diagram, and all you really need to know is the further you are away from this point, the worse it is. So, and the big red dot is the default configuration of the current version of CESM. And each of the black dots is one member of a perturbed physics ensemble. And the majority, we don't have sea ice in the tropics, it's not that fun. But the majority of the models are doing worse than the default configuration of the model. And if you looked at them in detail, if you looked at the variability, or you looked at the climate in different regions, you could probably eliminate them. A small fraction of the models assessed in this sort of this bulk way. This is a way of evaluating the root mean square error and the standard deviation of the models in a sort of bulk sense over the entire domain, global domain of the model. But there's a small number of the models which are comparable in the perturbed physics ensemble with the original, or with the default unperturbed version of the model. And so clearly we should be looking at those, whatever we do in our analysis, we should be looking at those configurations of the model in priority to the versions of the model which we can instantly disregard, and that needs to be factored into our analysis somehow. And so you can do this in various different ways. One way which I actually quite like, Danny Williamson at Exeter has been championing this recently, is just looking at high-dimensional plots of your parameter space and the performance of the models within that parameter space. So in this plot, each plot is one parameter against another parameter, and the warmer colours are the models which are doing better, effectively, or the models which are closer to the observations. And so what you can do with this type of approach, and he's used an emulator here, so he's used an emulator to densely sample the whatever 6-7 dimensional parameter spaces he has. But he uses this to produce a volume in the parameter space of versions of the model which are plausible. and then using that, you can say, okay, anywhere within this is a plausible version of the climate model. We'll just take those and then run future simulations with those plausible versions of the climate model, and that's perfectly acceptable, actually. That's a perfectly nice way of sampling uncertainty. It doesn't get confused. You don't need to choose a prior. You can just say, well, each of these versions of the model we can't rule them out, so we can consider them, perhaps choose different versions of the model which aren't too similar to each other. You're done. So there's a lot to be said for this. And it also allows you to represent rather high dimensional information. So if you say that we have 3 versions of the model which lie within the yellow section of the plots, and then we take those as 3 different configurations of the model, which we then submit as alternative configurations, this is perfectly acceptable and a nice way to sample uncertainty in a climate model. Sure.
On the back, last one. So in your previous slide where you had the Taylor diagram, you had a cluster of points which are right next to the red dot.
Right.
Right. So if you looked in this space here, are all of those points right at the highest yellow point, so that they're very close to each other in sort of the general sense of the parameter space?
Yeah. I mean, if you chose a metric such that it was equivalent to the distance in the Taylor diagram, then yes, it would be identical. I mean, it depends. If you use the same metric, then yes, the yellow dots would be the points which were closer to the observed point in the Taylor diagram.
It slightly depends upon the metric that you're choosing.
Absolutely depends on the metric. Yeah.
So maybe I'm misunderstanding, but in this case, is he only varying one parameter at a time, or can you vary multiple parameters together and still get a similar plot?
He's varying multiple parameters at the same time here.
Okay.
So the plot. So yeah, his original ensemble was Latin hypercube sample of the Hadley Center model. Use that to train an emulator. Sample the model space really densely, and then each one of these is one parameter against another parameter. So each one is a slice through parameter space.
Okay.
And so these kind of plot is a nice way of sort of visualizing the codependent behavior of parameters on a one-by-one basis. So you can see relationships between 2 parameters at the same time. You can't see relationships between 3 parameters at the same time. If that makes sense. So that's one thing you can do. Another thing you can do, and this is more useful if you're trying to find a low dimensional piece of information like climate sensitivity or the temperature of the June, July, August climatological temperature of the Southwest US between 2080 and 2100. This is good for just one number. But what you can find is that there might be emergent constraints in your ensemble, relationships between something which is potentially observable in the ensemble and something that you want to know. So there are a few examples of this from a few years ago, but so this was with Climate Prediction Net Ensemble, which is a very large ensemble of climate models using the Hadley Center, a previous version of the Hadley Center model, and the advantage of that, it was run at a relatively low resolution with a relatively small amount of output, but there were tens of thousands of simulations. So in that ensemble, if you looked at the seasonal cycle of temperature in a given region, you often found that there was a relationship Reto Canuti found that there was a relationship between the climate sensitivity of that model and the seasonal cycle in the present day of certain regions in the model. And so this is an example of an emergent constraint. So because we can go out today and measure what the seasonal cycle is here. And if that's related in the ensemble to what the climate sensitivity of the model is, that gives us some constraint on eliminating some of the very high values of climate sensitivity in this ensemble. This was a more complicated version of the same thing, which used lots of different observations at the same time to constrain the overall feedback in the model. But you have to be careful, because if you use an approach like this, which effectively assumes that there is a relationship between this thing that you can observe and this thing that you don't know, then you're implicitly assuming that the real world obeys this relationship, or another model would obey this relationship. And this is something you can test. I think I've got my slides the wrong way around. Yeah, here we are. So this is something you can test. So say that you did the same thing, and on this axis here, you made a prediction based on things which you can observe in the model, and you made a prediction of what the climate sensitivity of a given model would be. And then you plot that against what the actual climate sensitivity of that model was. You found a very good relationship. So this is effectively repeating the second plot, which I showed before, the Piani plot. So you find this nice relationship between the thing which you predict, and this is taking aspects of the present day climate, like distributions of sea surface temperatures and profiles of relative humidity, which you can go out today and measure, make a prediction of the climate sensitivity, valid within the ensemble. The problem is when you then try to apply that, so you have that relationship, you're happy with it, but then you try to apply it to a different climate model and then try to predict what its climate sensitivity is. You find that it's consistently biased. So this relationship which you found within the perturbed physics ensemble is unique to the relationships which emerge in that parameter perturbation experiment. And so if you apply it to a completely different set of physical assumptions, which might be in a different climate model, so different climate models don't have the same parameters. They make completely different assumptions on how to represent the sub-grid scale behavior, how to represent convection, make completely different assumptions on when convection happens, for example. And so these relationships which are robust within the ensemble are not robust when you apply it to the NCAR model, for example. This is taking the results from one perturbed physics ensemble and applying it in the green dots here to another perturbed physics ensemble, where it completely fails to get the range of response. It predicts that half of the NCAR ensemble should have a very high value of climate sensitivity, and it doesn't. So you have to be careful. And so any analysis which you do has to be aware that there are systematic differences between different climate models, and you can't assume that relationships in a given climate model and a given perturbation experiment are universal. And so that has to be hard-coded into your result. So if you followed a Bayesian methodology, and you've started with this is your smooth distribution, which you've got by sampling your parameter space with some prior which you thought was sensible. And then you've updated that prior and then you've effectively weighted your distribution by the results which you think are more plausible, by weighting them by their skill in producing the present day. You still yet haven't accounted for this problem of model discrepancy. You're still assuming that this relationship up here, this relationship between the future and a given set of parameters, you've assumed that that's universal, and that this relationship is applicable to the real world. And so you need to find some way, if you want to be really confident in your result, or you don't want to be overconfident in your result, of representing the fact that that these relationships may not hold in the real world. And that's what this slide is basically showing. You need a discrepancy term, which says that as you integrate over your parameter space, so this bit here is effectively your climate model. This is saying you run your climate model with a given set of parameters, you get a given future. You need this discrepancy term, which somehow needs to represent the uncertainty in the fact that this might not actually be the case. And so that's what UKSIP did. And they got this discrepancy term by using the CMIP models and then applying their methodology without the discrepancy term to to each of the models in CMIP, taking each one of them as truth, and then working out a term which could account for both the bias and the additional uncertainty which you get by assuming that each of these models is truth, and what error you get in your prediction of the thing you're interested in. And so from the weighted, so this is only considering the error in each of the perturbed climate models. When they consider the systematic component, they shifted their result. This isn't the only way of doing it. This isn't my way of doing it, but this is how it was done in this experiment. And the paper is very long and complicated, and go and read it if you want to know in detail about what they did. So perturbed physics ensembles are useful, and they're necessary in terms of you shouldn't assume that the output of a given climate model is unique. And it's wise to sample the diverse range of potential and plausible outcomes which you can get from a given climate model. But there's a limit to what you can do, because in each climate, a climate model contains a set of assumptions which are not represented within parameters. So they contain a set of assumptions which are at the process level. And these can be massive, and they can be significant, and they can vary from one model to another. And so the only way that we really have to assess this at the moment is the multimodal archive like CMIP. And just as a perturbed physics ensemble has plenty of caveats that you should have when interpreting its results, arguably the CMIP is almost a bigger can of worms, because as it's been coined an ensemble of opportunity, it's not an ensemble which is designed to be an optimal sample of the possible futures that we might get. It's just what people happen to produce and what people had the computing time to produce. And there are all sorts of caveats associated with that. Some models are associated with other models. Some models branch off other models. Some models are much worse than other models. And you don't need, but if you're going to assess uncertainty in your projection, in our projection, from CMIP, you need a way of accounting for all this. So firstly, let's talk about why we can't just use perturbed physics ensembles let's look at a way that we can assess that given only the output of those ensembles. And there's this idea which came from the group at Jamstec, which is building on an idea which has been used in, Jamstec, Japan, in Yokohama. It's James Annan's group. James Annan's now retired, I think. But this came out of his group. And it's borrowing on an idea which is used regularly in weather forecasting. And that's the idea of whether your ensemble is over dispersive or under dispersive. So we'll take a second to see what that means. So say that you had 5 different regions which you were interested in your climate model, or in your projection. And you say you have an ensemble which is all of these blue dots. And then you go out and then you measure what the temperature is in each of these 5 regions over some long period. So you're representing the climatology somehow. And then you look at what this temperature is in each of your climate models compared to what it is in the observations. What you want, ideally, is an ensemble where the observations are just as likely to be at the bottom or in the middle or at the top of the ensemble. So if you look at the rank, so this is the rank of where the observations fall within the ensemble. You want it to be equally likely to be 1, 2, 3, 4, or 5. That would be perfect. That would mean that your ensemble is correctly assessing the uncertainty or that the observations are a plausible member of the ensemble. Or you could interpret it that way. What you don't want is a situation like this. So this is an under-dispersive ensemble. In this case, the observations always fall outside the ensemble in every case. And so you get this case where the observations, if you rank them all up, would always be 1 or 5. This would be an optimally under-dispersive ensemble. So this means that you haven't sampled uncertainty enough in your ensemble. All of the models look like each other, but none of the models look like the observations. This is a bad state of affairs. But an equally bad state of affairs is an over-dispersive ensemble. In this case, you have lots of terrible models, which come far outside the observations on both sides. But the observations always fall right in the middle. This means that your assessment, if you just look at the spread of projections which you get in the future, possibly, that the spread which you'll get is possibly greater than would be appropriate, and you could probably eliminate some of these ensembles, these ensemble members. The reason I bring this up is because there's a big difference in if you do this both for a perturbed physics ensemble and you do it for an ensemble like CMIP, you get very different results. So CMIP, each one of these takes a different variable, so they did this in various different ways, looking at various different outputs of the model. And it's pretty much flat for most cases. But if you look at the output of a perturbed physics ensemble, it looks much more like this case, the underdispersive option. So that means that in a perturbed physics ensemble, although you're changing the parameters in the ensemble, they still pretty much look like the default model in the ensemble, much more so than the diversity which you get in CMIP. So what this paper was basically saying is that there's a type of diversity which you can only really get from a multi-model ensemble. You can only get so far by perturbing parameters in a single model. You have to do both. So we have to look at the multi-model ensemble, and it's really complicated. So this is a simplified history of the models which are currently available in CMIP today, which I haven't quite updated to 2013, but you get the idea. The blue lines show the direct evolution of a given model. The orange lines show when that one model had fragmented off another, or when a significant part of one model was used for the creation of another model. And along the bottom are all of the models which we have available today in CMIP 5, or some of the models which we have today in CMIP 5. And so this is a very interbred collection of things which we have at the bottom. And so if we just considered each of these models to be entirely independent, that would be an incorrect assumption. Because in many cases, quite a large fraction of the actual code within a model are actually lifted directly from a different model. Sometimes it's not quite as bad as that. Sometimes it's more difficult to detect, and just the same assumptions have gone into the construction of different models. And that's arguably almost as bad and much harder to find out, actually. But we need, if we're going to consider the distribution of results which we get from an ensemble like CMIP to be representative of uncertainty, then we need some way of accounting for this. We need some way of accounting for this interbreeding of climate models. Luckily, you can actually do this quantitatively, quite successfully actually, using the output of the models themselves. So this is a paper by David Masson, who was at ETH and is now, I don't know where he is now. He's not there anymore. But this basically showed that purely by looking at effectively the root mean squared difference, pair difference between different models in the CMIP 5 archive, you can recover quite a lot of this family tree. So the way that this plot is created, you start reading it from this end, and then the two models which are closest together, in this case are the two versions of the GFDL model, they are combined into a single model. And then you repeat this until you only have 1 point left. And so what you're able to reproduce is effectively quite a rich structure of the family tree of the models which we have in the archive. And invariably, it gets at relationships which make sense from a physical point of view. So trivially, when we have two different models run at a different resolution, they should be very similar. They have the same physics, they have the same parameterization. No, they don't always have the same parameterization values, actually. But you should expect them to have lots of things in common. And this approach, just simply looking at the root mean square difference between two different models, can pick that up. And so this makes for a pretty diagram, but it would be good to have a way of formally using this type of information to assess the uncertainty in our projections. And so we'll talk about that in a minute. Yeah.
Temperature? What, is there an error of what?
That was just temperature.
Okay, making sure.
Yeah, so that means this plot is really simple to produce. So you just look at gridded temperature output, regrid them all to the same same resolution, and look at the root mean square difference between different models. Look at the two which are closest to each other. They will be the same model at different resolutions. Yeah, and you can do it with precipitation as well. It works. So one way you can get at producing projections or increasing your confidence in projections from a multi-model ensemble, in some cases, is to do something like this. And we alluded to this before with the seasonal in the perturbed physics case, with the seasonal cycle and the climate sensitivity. But in some cases, this works with the multi-model ensemble as well. So the example which everybody always shows when they refer to this kind of thing is this. And you should note that they always show this plot because it means that it doesn't work for anything else. This is the relationship between the seasonal cycle of high latitude albedo in the models in the CMIP3 archive, and then the level of high latitude albedo feedback you get in the future. And they're very closely related. And you can improve your estimate of high latitude albedo in the future by constraining it by looking at the current values of the seasonal cycle. Now, there are lots of reasons why this works in this example, and that's because it's the same process which is manifested in both cases. So the processes which govern the ice albedo feedback in the model is the same for the seasonal cycle and for the change in the future. And so you get this nice one-to-one relationship. And you might, and people have tried and treat a more complex future behavior of the model in the same way. And this is what this paper, which is Fasulo and Tremberth from last year, tried to do. And argued that they were correct and able to do so. But you should be careful. So what they did is they found a variable in the present day simulation of the model, which was the subtropical relative humidity over a given latitude band over oceans, and then found that it correlated quite well with climate sensitivity in CMIP3. It didn't correlate quite well with sensitivity in CMIP5, just as an aside. But you get a regression coefficient of 0.7. Now, these things appear to be related. But you have to be careful, because our sample size in CMIP3 is not, and CMIP5 is not very large. Even if you considered all of the models to be independent. In CMIP3, you had 20 models. In CMIP5, maybe you have 40. But of course, they're not independent because of the all interbreeding relationships which we were talking about before. And so your effective number of models is probably much smaller than that. And so when you get a regression coefficient of 0.7, it doesn't necessarily mean that, that you really have a physical relationship between the two things. And you better have a physical relationship to be able to back it up. So to belabor this point, this is a paper by Peter Caldwell this year, which tried a brute force approach for looking for relationships between observable things in the CMIP5 ensemble and climate sensitivity. So what they found, and they tested, firstly, if you look at the blue bars, or whatever this color is, these are the number of fields, and he looked at lots of different variables over lots of different domains. The number of fields which correlate at different levels with climate sensitivity. So this bar is all the variables which correlate with a regression coefficient between 0 and 0.1. So there's tens of thousands of them. And then critically, once you get to the 0.7 correlation which we had for the Fasulo and Trentworth paper, we get maybe 15 variables which correlate at 0.7 or above with climate sensitivity. And then what we did was we looked at what if you randomize the values of climate sensitivity and looked at what the relationship was between effectively now random numbers and the variables in the ensemble. You get the purple bars here. And so sorry? Marv, yeah. Puce. And so what you find was that even if your values of climate sensitivities are entirely random, you still expect probably to get some variables which correlate at 0.7 or greater with something in your archive. And that's because if there are tens of thousands of degrees of freedom within the ensemble and you only have effectively maybe 15 models, then at some point you're randomly going to get something which correlates at 0.7. What you actually find is that you actually do get more with more fields which correlate with climate sensitivity than with the random vector, especially at this 0.7 level. But then what he went on to show was that this goes away if you remove both the covariance between different fields. And so remember before, there was no attention given to whether one field would naturally covary with another. So you would expect, if you take two adjacent grid cells in the middle of the Pacific, they're not independent. So you should take those out. And so that's what the first plot shows. So you take out the fields which covary with each other, and then you show that the amount of the amount of fields which you expect to get by chance comes more into line with what you find with the fields correlating with climate sensitivity. But you need to do two things to actually get it to line up completely. And then you have to eliminate the covariant models as well. And once you're down to 15 models, then the number of variables which you get correlating with climate sensitivity is entirely what you would expect by pure chance. So
Ben, you've got about half an hour left.
Okay.
General questions.
Three slides.
Okay, 3 slides.
Yeah.
How did you calculate that there are 10,000 of degree of freedom in the CMIP5 ensemble?
No, there aren't 10,000 degrees of freedom. No, I did say that, and that's wrong. There are 10,000 fields which were used for this experiment. The number of degrees of freedom, you could assess that in different ways. You could take principal components of the output. You could, but no. Your assessment of this is always limited by the number of samples, number of models which you have. Yeah. Yeah. Sorry, I misspoke. So finally, some ideas for what, these are some papers which are just submitted on what we might be able to do practically to attempt to address these problems of interdependency. And I went out, the co-authors and I went out to have a methodology which could do two things. And it could be defined simply. The first is that if you have a methodology which produces some estimate of, or some distribution for future climate change, then that methodology should be insensitive to adding another model which is exactly the same as a model which is already in the ensemble. It sounds trivial, but often it's not the case. And the second thing is your methodology should account for model skill. So if you add a model of Venus to your ensemble, that shouldn't change the result either, because that model should be so bad and so match up so poorly with the observations which you have of the state, then that shouldn't change the distribution of models you have to go forward with your projection. And again, we use this idea of distance between two models, or pairwise distance between models as our basic data set. And this is a very data-rich thing. So this is just a subsample of a set of models from CMIP 3 and 5, just so you can see the kind of relationships which you expect to find. So the colors represent the distance between two models. Warm colors represent a large distance between two models. And this is a distance in a multivariate sense. So this is taking temperature and precipitation and top of atmosphere radiative fluxes. And you and then you can produce a Euclidean distance once you've reduced the dimensionality of that space in an appropriate way, which I won't go into now, but if you want to talk to me afterwards, that's fine. And so you get these structures. So like, for example, if you look at the models which come from the Hadley Center, they're all dark, cool colors, which means they're very close to each other in the space which you get using this approach. And the same for the GFDL models. But then you get some models in red, which are red all the way across the line, which means that they're far away from every other model in the ensemble. They're just an outlier. So these points, these models look very different in lots of different ways to models which are in the rest of the archive. And so this is quite a rich piece of information which we can use in various ways. The first thing we can do is say that the distribution which we get is not the type of distribution which we would get by chance. This seems seems an obvious thing to say, but we can now say it quantitatively. So this is the black bars here are taking all sorts of different entirely random ensembles constructed in a space in the same way as we've reduced the space of for our analysis before. So it's a 15-dimensional space, and the models are represented in a 15-dimensional space. And then we consider random Gaussian distributions of models, and then look at the difference between which we'd expect by chance. And so those are the black bars here. And so we have some points here in the actual CMIP archive which are closer together than you would ever expect to get purely by chance. And so we have an ensemble which doesn't look like it was constructed randomly, which is perhaps obvious, but we can say it. But then we can use this information to construct a surface of models which we might get if we were able to interpolate between the results of different models in the archive. So that's what this plot shows here. So the distances between the models in this plot, and I've omitted the code on which model is which, but each of these colored circles and diamonds are models from a different institution. Models of the same color are from the same institution. So these are all the GFDL models here. These are all the NCAR models here, Hadley Center models here. So we can represent these intermodel distances with some approximation in a lower dimensional space, and then interpolate the thing which we're interested in between the different models in the archive. And this way of representing things has some advantages, because remember before that we had this requirement that if we added the same model to the ensemble twice, it wouldn't change the results. This follows that. So if I added this model twice, it would just be another point here. It wouldn't change the interpolated surface, which we're then free to sample any way we like. We can choose different priors which either are centered on the observations, or we can assume that the entire space is equally plausible. We can sample those distributions in a way which is perhaps less subject to the random elements of CMIP, the fact that some models are replicated more than others. So this is less sensitive to that, potentially. And if we repeat this, because this is not an exact solution, we can produce various plots which look a bit like this, with slightly different initial conditions. This is called multi-dimensional scaling, taking a 15-dimensional space and then mapping it onto a 2-dimensional space. The results are approximate. But we can do it lots of times, and then interpolate the things which we're interested in this case, climate sensitivity, over the space. And then we can produce distributions, smooth distributions for the thing which we're interested in. Which arguably satisfy this idea that that replicated models are dealt with, and models which are very similar to each other are not given too much weight. And the other thing we can do is just simply eliminate models. And so that's what this plot shows. So we start from the far left of the diagram, and we choose models which are most similar to each other, and then we eliminate them, and then choose of the two, we choose the better performing model and allow that to persist. And then you continue until you only have one model left. And at some point, you stop when you're happy that you still have an acceptable amount of model diversity, but you have and an acceptable amount of model replication. And that's a subjective choice, but this gives you a framework for model elimination, which starts with models which are overrepresented in the ensemble. And I'll stop there and talk more about that on one-to-one basis if you're interested.